actually going to do a walkthrough through the assignment to help any students that might be struggling over the weekend and into next week. This is the homework 2 PDF. It is due February 1st at 11:59 p.m. The homework is broken up into two parts, a written part and a coding part. The written problems are to be submitted to Gradescope as well as the coding part. So to get started, let's give some, the very first problem essentially asks you to write the functions below that are O of n squared. So you are giving 7 functions, g1, g2, on to g7. And for each of these functions, you need to determine, we are expecting a list of the functions which are O of n squared. Things to keep in mind here is that big O is an upper bound. What does that mean? That means that n is big O of n squared. It also means that 1 is big O of n squared. N minus 3 is big O of n squared. In fact, n squared is big O of n cubed. N squared is also big O of n squared. The reason for this is that big O is really saying an upper bound. So intuitively, what each of these are saying is that for big enough n is less than or equal to n squared. Here, for big enough n, and in fact, for all n, 1 is less than or equal to n. For n bigger than 1. Similarly here, you can actually see that the for big enough matters because n minus 3, let's actually change this to let's say n plus 10. N plus 10 is smaller than or equal to n squared for big enough n, but not for the first few values. For the first few values, this is actually going to be much bigger than n squared, right? So for n equals 1, this is 11. And 11 is actually bigger than n squared, which is 1. So it does matter that we're looking at for big enough n. So essentially it's saying that once n gets big enough, n squared is going to be much bigger. Similarly for the rest of them, I would suggest something that can help you with this assignment is pulling up Wolfram Alpha. So you can actually very directly type in plot sine n plus 5 and n squared from 1 to, let's say, 10. So you can get a sense of what these functions look like as they get bigger. So if you plug this in, you'll actually see that the sine function is bigger than n squared at the beginning, but sine is essentially bounded above by 1, while n squared goes on to infinity. So it should be pretty clear that sine of n, at least, is big O of n squared. That is to say, sine of n is big O of n squared, and that's because sine of n is smaller than n squared for big enough n. Great. For part 2, we're going to jump a little bit more into the formal definition of big O. So again, how do you prove something is big O? Is you essentially have to prove that your function is smaller than the big O function times a constant for values for your input values that are big enough. So for the first one, you are actually asked to use c equal 1. So essentially what we want, if we plug in everything that we're given in the problem, you'll see that f of n is 6n. And you'll see that g of n is n squared minus 3n. Squared minus 3n. And what we want to be true is we want that 6n c times. We want to figure out what is the n0, because that's what we're missing, such that for n bigger than n0. So we need to find the n0 such that for all n bigger than n0. So once n gets big enough, this is true. And we are given that c is equal to 1. So if c is equal to 1, that means that c of n needs to be less than or equal to n squared minus 3, n. That's c equal to 1, because c is equal to 1. That's given to us. So now here we can actually just work out a little bit of math. We can divide both sides by n, and we'll get that 6 is less than or equal to n minus 3. So you can see I'm dividing, I essentially factor out an n, and then I divide both sides by n. And why can we do that? We can do that because we know that n is, we always assume n to be bigger than 0. So it can never be 0, so we can divide by n. Now, if we move some stuff around, we add 3 to both sides, we actually get that n must be bigger than or equal to 9. N bigger than or equal to 9. Only in this case is it true, right? So as we worked, only in this case, only if n is bigger than or equal to 9, is it true that 6n is less than or equal to n times n minus 3. So that actually gives us a value of n0. For example, we could take n0 equal to 9. There are other values you can take, n0 equal to 10, 11, 12, they all work. Now, this is the work that you did to get the answer, but the way you would write the formal proof is you would say, using c equal 1 and n0 equal to 9, we have that for all n bigger than or equal to 9, by definition, 9 is less than or equal to n, right? So this is by definition, by our assumption, not by definition, right? This is for all n bigger than or equal to 9, 9 is less than or equal to n. Now, we subtract 3 from both sides, so we get 6 is less than or equal to n minus 3 by subtracting 3. Then we get 6n is less than or equal to n times n minus 3 by multiplying both sides by n. And finally, that gives us 6n is less than or equal to n squared minus 3n. But you will notice this is exactly what it means for 6n to be big O of n squared minus 3n. So we have formally proved that you can actually use c equal 1 and n0 equal 9 in this first proof. The second proof is very similar, except what happens now is I give you the n0, and your job is to find a c that works. So again, your answer is actually this. This is the proof. This is the proof that actually walks you through all the steps. This is the work you had to do to figure out what value of n0 to use. So for this next one, again, this is what we want to be true. And in this case, we are not given c, so we keep the c around. But we do know that n is bigger than or equal to 4. So again, if we try to simplify, because essentially we want to solve for c, you can actually imagine working backwards here. So you know that n is bigger than n0. That's given. That means that n is bigger than or equal to n0, which is equal to 4. So that means that n is bigger than or equal to 4. If we subtract 3 from both sides, we get that n is bigger than or equal to 1. Right? So this is subtract 3 from both sides. We get that n minus 3 is bigger than or equal to 1. If we then multiply by n, we get that n times n minus 3 is bigger than or equal to n. So this is multiply by 3 on both sides, which if we simplify becomes n squared minus 3n is bigger than or equal to n. Now, what we want, this is very close to what we want. What we want is 6n is less than or equal to n squared minus 3n. So you can see here that we're just a little bit off. So what we can do actually is we can multiply both sides by 6, right? So if we multiply both sides by 6, we actually get 6n squared minus 3n is bigger than or equal to 6n, which in fact gives us a possible value of c. This is my c. My c in this case is 6. We have now figured out that for n bigger than 4, the below is true. Okay. Continuing on, this is more practice with big O. We are essentially asking you to compare, to figure out which statement is true and to mark them accordingly in the box. So for example, the first row is asking 3 questions. Is log n big O of n? Is log n big omega of n? Is log n big theta of n? And the way to think about this is big O, as always, this is less than or equal to. It's an upper bound. Big omega is the lower bound. So it's essentially flipping big O. And big theta is both. So something that you'll probably notice is that if you're big O of something, you cannot also be big omega of something. Or like if you're big O, sorry, that's actually incorrect. If you're big O and you're big omega, then you must be big theta. You must be both. So if a row is both big O and big omega, actually all of the columns are filled. However, if you are not both big O and big omega, you cannot be big theta. Therefore, for the rest of the columns, only one will be filled. We can walk through a few of this together, but again, essentially, the first row is asking this, and it wants you to check whichever is true. The second row is asking 2n cubed is big O of 2 to the n. 2n cubed. It's asking the same questions, but for a different function. And something to note is that exponential functions grow very fast. So again, if you jump back to your Wolfram alpha, you can very easily plot, let's say 2 times n cubed and 2 to the n. And you will see that from 1 to 10, let's say, you will easily see that 2 to the n actually appears to be lower than 2n cubed. But don't be tricked. If you go bigger, you actually see that while 2 to the n, which is this purple line here, there is below 2 times n cubed, which is this blue line here, eventually it is above. So for big enough n, 2 times n cubed is big O of 2 raised to the n. For the rest of them, you can work the same thing. One hint to keep in mind is that for logs, there is a change of base formula. So if you have log base b of a, this is actually equal to log base c of a divided by log base c of b. So essentially you can change bases. So what normally you would do is you would replace this with log base 2. So even if you, for example, let's say you had log base 10 of n, this is actually the same as log base 2 of n divided by log base 2 of 10. And this is just a constant, okay? For the last one, something to keep in mind is there's some exponent rules. So for example, 4 raised to the log base 2 of n is actually equal to 2 squared raised to the log base 2 of n, which by exponent rules you can actually rewrite as 2 raised to the log base 2 of n squared, which this 2 raised to the log base 2 of n cancel out, so simplifies down to n squared. All right, moving on. Third exercise. Here we're going to practice with recurrence relations. So again, I summarized the Master Theorem. Essentially what you want to do here is you want to identify the values of A, the values of B, and the values of and the value of D. So in our situation here, for example, for the first one, so for A, we actually have a value of A equal to 18, a value of B equal to 9, and a value of D equal to 1/2. 1 divided by 2. Why is that? That's because the square root of n is the same as n raised to the 1/2 power. For B, we have A equals to 5, B equals to 4, and D equals to 2. So essentially, once you have figured out the A, B's, and D's, you would plug them into this formula to see which case you fall into. For example, in this second one, we have A equals to 5, and we have B raised to the D, so that's 4 raised to the 2 squared, that's equal to 8. So that means that actually A is bigger than B to the D. So you actually fall into the second case, which then directly gives you the big O running time. For the last one, we're practicing with modified merge sort. Here, I want you to read the code and write a recurrence relation and then figure out the big O running time. So if you're looking at this code, you'll see merge sort thirds. We can walk through it in detail, but essentially the first thing we do is we compute the size of the vector, which is done in constant time. If the vector is less than 1, we immediately return. If the length of the vector is less than or equal to 1, we immediately return. Then we call ourselves 1, 2, 3 times. So our recurrence relation is going to be something like T of n equals. We're going to call ourselves on something 3 times. Okay? And then at the end, after we call ourselves on something, we actually call merge here, and we call merge here. So we know merge takes big O of n time. And we call ourselves twice, so we could say, this is 2 times big O of n, but big O swallows constant, so it's just a normal big O. So even though we're calling ourselves twice, actually, one question to answer is it might not be n. But here we call ourselves twice on some input of some size. So now we just need to figure out how big are the sizes. So for the first recursive call, we seem to be calling ourselves from the beginning up to n divided by 3. So the size of this vector is n divided by 3. For the second one, we seem to be calling ourselves from n divided by 3 up to 2 times n divided by 3. So again, the size of this vector is n divided by 3. And for the last one, we call from 2 times n divided by 3 up to the end. So again, the size of this vector is n divided by 3. We can actually, because these are all the same, we can write it as this 3 times. And then for the last one, we're merging left, middle, and then we're merging temp and right. So intuitively, because we are calling ourselves on a smaller input, that's only a third of the size, we expect the right, middle, and left to each be a third of the size. So this is actually O of 1/3 n plus 1/3 n. But again, these are just constants, so they don't matter. So it actually ends up being O of n. So here is a recurrence relation with A equals to 3, B equal to 3, and D equal to 1. That means that 3, which is equal to A, is actually equal to B raised to the D, which is equal to 3 raised to the 1. So actually that gives you the case that you want to look at in your merge sort in your master theorem equation. Let's take a look at the last section. So this is section 5 of the written assignment. Here what we're asking is for you to determine the big O running time of each of these functions. So a couple of things to keep in mind is that this function is given an input, okay, of some vector of a particular size. Now we start a loop at 1, and each time, instead of adding 1, this is the tricky part, we actually double the size of the loop. So let's walk through a few examples and see. So if my input is of size 1, how many times does the loop run? Answer? 0. Because you'll notice we start I equals to 1, but I is not less than input that size. So it actually runs 0 times. So let's try a few more examples. If my input is of size 2, if my input is of size 4, if my input is of size 8, and if my input is of size 16. So for an input of size 2, our for loop runs once, because it'll first check if 1 is less than 2, which is true. And then it'll multiply I by 2, which means I will become 2. And then it will check if 2 is less than 2, which is not true. For an input of size 4, it actually runs 2 times. It'll first check, the first iteration, second iteration, it'll multiply 2 times 2, which will be 4, and it will not run again. For an input of size 8, it runs 3 times. And for an input of size 16, it runs 4 times. You can continue this pattern, but hopefully, essentially, what you're trying to do is what function, when given 1, it gives me 0. When given 2, it gives me 1. When given 4, it gives me 2. When given 8, it gives me 3. And when given 16, it gives me 4. For a hint, look at logs. Continuing, next part of the function, we have do something else. So again, this is a very similar function. Let's see what it does first. It takes the input. It gets the size of the input, which is z, prints z, and then while z is bigger than 10, it prints that value, and then it divides z by 10. So intuitively, how many times does the while loop run? Well, how many times can I divide z by 10 before it is less than 10? Is there a function that answers this question? That's my hint for this one. Continuing next, we see fun with recursion. So we have another tricky question. I think something that will help here is just to walk through a few examples where we look at the input and we see what size it is. So let's say that our input size was 1,000. Let's say that our input size is 6, and let's say that our input size is 14. So for the 1,000 input size, it'll first check to see, well, let's try something easier. Let's say our input size is 50. So for the 50 case, it'll first check to see if it's divisible by 7, which it's not, in which case it'll remove one element and then call itself. So while this function is recursive, it'll be helpful for you to think through what actually happens. So it calls itself now on 49. Now, the next time 49 is in fact divisible by 7, so it immediately returns. So this function called itself twice, and each time it did constant work. O of 1. Okay? So this function with input 50 was constant. With input 6, it actually calls itself to go to 5, to go to 4, 3, 2, and then 1. And finally, it gets to 0, in which case 0 is divisible by 7. So it actually calls itself 7 times. Still, each time it does constant work. So this is actually O of 7, which is O of 1. All right, that's probably about the hint that I'm going to give for this one, but I do want you to think, how many times does it call itself? Does it matter if the input is 1 million? Is it going to call itself 1 million times? You know? Or might it call itself less? What if the input is 7,006? How many times will it call itself? And again, the final hint is if a function only does constant work no matter the input, then it is big O of 1. Function only does constant work. That is big O of 1. All right, let's jump to the coding, which is the last part we're going to cover. So the coding piece, you should be able to click here to open up a replit where folks are working through the code. I'll pull up here the homework 2 code. In this homework, you want to look at the README. The README is going to walk you through some of the problems that we have. A couple of problems that we're looking for first. The first one is count sevens. So something we can do is we can actually write a function, for example, that counts fives. So if we had a function, let me set my syntax to C++. Let's find a function count fives, which takes as input an integer. How would we do this recursively? Count the number of fives recursively. Well, intuitively, there's two cases. You want to break your input to be smaller. So you don't necessarily have to break it into halves. You could do it that way if you wanted. You could count the number of fives in one half and the number of fives in another half. The easiest way to do this is to look at the very last digit. So the way we do that is we can say int digit equals n mod 10. This is going to give us, so for example, if we have 281, this is going to give us the 1. Int leftover is going to be n divided by 10. So this is going to give us whatever is left over, right? Then we can simply check if digit is equal to 5. Then our total is going to be 1 plus how many ever fives are left in the leftover part. Otherwise, we just count the number of fives in the leftover part. Now, one thing to keep in mind is we also need a base case. So the simplest base case here is if n is equal to 0, then there are 0 fives. Now, why is this base case sufficient? Because since you're always dividing by 10, you will always get to n equal to 0. So eventually, your function will end. Now, the next problem is one asking you about picking berries. Something to keep in mind here is that you essentially have two decisions to make. Let's write the pseudocode for this. So let's say pick berries, and you're given the input is going to be a vector of values. And we want to do this recursively. So the first thing we want to think about is that I either pick the first berry bush or not. So let's cover both of those cases. So if I do pick the first berry bush, then the number of berries picked is going to be given by my picking that first berry bush plus how many ever berries I can pick if I don't pick the next bush and don't include, because I've already added my first berries here. So this is saying don't include this 0 and don't include the next bush because I can't pick it anymore. Okay. The other option is I don't pick the first bush, in which case num berries other is just going to be pick berries of values 1 onwards. Right? Does it make sense? So I look at the next berries. I don't pick the first bush, so that means I could pick the first one, so I only look at everything left over. And then finally, we're trying to find the maximum number of berries we could pick. So we want to return max of num berries and num berries other. So this is the pseudocode that you might come up with in order to solve this problem. The one thing that we're missing, of course, is base case. So in this case, for the base case, there's actually 2 base cases. If you notice here, we actually call ourselves, we assume that values is bigger than or equal to 2. So our base case actually corresponds to if the len of values is 0. So if it's empty, then we cannot pick any berries. So let's return 0. If there is only 1 bush, then let's return that bush because we pick it. Well, I guess technically here you could say the max of that bush and 0, because I guess if somehow your bush has negative berries, you might not want to pick it, even though it's the only one. And that's basically it. So you would write this function. You'll end up writing the code for these functions in count 7s and pick berries. We did an example for count 5s. Count 7s is very similar. And pick berries is here. This is the pseudocode.